Hi everybody, welcome back to the Feynman technique. Today we're going to be developing a new integral formula using Feynman integration, aka differentiation under the integral sign. All right, so this is the integral that we want to develop a formula for, right here. All right, so the x in the denominator is the main obstacle, of course. It prevents standard integration techniques. And for this, we're going to assume that b is greater than 0 for convergence purposes. All right, so the first step is we are going to take the derivative of our function with respect to a directly using the Leibniz rule for differentiation under the integral sign, which allows us to pass this derivative inside the integral as a partial. So evaluating that partial, the partial with respect to a of sine ax is just x cosine ax. So that's what we get. There's our partial, and you'll notice the x's cancel out. So we are left with just this. And this is a standard integral that you can evaluate using integration by parts. All right. So this is it. This is the standard result. This is the antiderivative that you find via integration by parts. It doesn't matter what you use as your u and your dv. You'll end up with the same answer. Okay, so this is our derivative of our function of a right here. All right. We are not interested in I prime of a. What we want is I of a. So what we do is we just anti-differentiate our expression for I of a that we just found. And anti-differentiating this with respect to a gives arctangent a over b plus c using standard integration techniques. So this is I of a. And we have this constant of integration that we almost always need to solve for when we're using Feynman integration. So the next step is just to remember that I of 0 is equal to 0. If we let a equal 0 in our original integral formula, it becomes sine 0, which is 0. So the whole integral is 0. So finally, we have that I of 0 is equal to the arctangent of 0 over b plus c. So c is 0. So our next step, well, that's it. If we let c equal 0, this formula just becomes arctangent a over b. So this is our formula right here. The integral from 0 to infinity of sine of ax over x times e to the negative bx dx is equal to arctangent of a over b. And there are a couple of useful special cases of this. For instance, the case where b is equal to 0 is going to give us that famous sine ax over x from integral to infinity is equal to pi over 2 for all a not equal to 0, of course. And there's also the special case where a is equal to b, giving us a value of pi over 4. All right, guys, I hope you enjoyed that, and we will see you next time.